So I'm streaming to YouTube right now, and let me see whether that's working or not. If you guys can confirm, you can just kind of type on the text channel too if you can see that it's working on YouTube. Should be working now. Yep, seems to be working. Cool. Alright. Okay. Alright. So looks like everybody's ready to go. Yes? Okay. Alright. Excellent. So YouTube streaming is on. I can actually see on my own screen. So if you are still having issues with Discord, go ahead and watch the lecture on YouTube. I do have to warn you, if you decide to use YouTube, is YouTube has a horrendous lag time. Discord is not too bad. I think it's acceptable, but YouTube has like 10 to 15 seconds of lag time, so that's not particularly useful for class purposes. Yes. Okay. All right. Use Discord if you can, and if you cannot get Discord to work, then go ahead and use YouTube. So that's kind of the deal. Okay, if you can, stay on Discord. Okay, because I think I can fit everybody into Discord, because I turned off the ability of you guys to use voice in the voice channel. So everything that you want to feed back to me, is going to have to go through the text channel, and I make one text channel for each day of the lecture. So let's try to stay on that particular text channel. All right. So I think we are ready to go. The syllabus, I'm not going to spend too much time to talk about it today because I already made a video, and you are strongly encouraged, should watch that video so that you at least understand my expectations in this class. So that's one. And let me start up something else. Okay, give me a second here. I need to get to one of my command line prompts. Okay, so let's see, what am I gonna do? Right, I'm gonna use free playing. So this is something new. I have not done this before, but I'm going to start to use free playing, as a mind map for certain things. And what I'm doing right now is I'm going to show you something that I might have shared already. I cannot remember because I'm teaching two classes. I'm pretty sure I shared this with my other class already, but with this class I'm not sure. Okay, I'm going to drag it into where you can see the recording. So this is a mind map, and basically just a whole bunch of bubbles connected by connectors. I want to focus particularly on how to take a class. Now I know you guys are already in CISP310 and you have taken many other classes already, but I really want to focus on the fact that during lecture it's really important to take notes. Okay, because from a discussion with my previous class, which is a summer session, a few students told me that when they are in the lecture, like when it's online but synchronous, they just listen to me. Well, I think most people really need to take notes. And when I say taking notes, it's not really just copying down whatever I say, because that's useless. Everything that I say, everything that you can see on your screen is already being screen recorded on YouTube. Okay, so you can always go back to that stuff. So what you're doing when you're taking notes is making connections between the concepts and then documenting those connections in your own mind, because I cannot read minds. Okay, so I cannot take notes for you. So only you understand what is going on in your head, what questions you might have, and what kind of connection you have been making during the lecture. That is what you need to do when you take notes. Now, taking notes also means it is important to preview a class. Now, obviously, this is the first lecture, and it's pretty difficult for people to pre-read the material. It is possible because all the written material for this class is already published. But most people, did not, understand that it's important to do it. So from here on, I would just say that it's important to pre-read the material of a particular lecture before the lecture, and then you can start to jot down questions, okay, as you are pre-reading or previewing the content of a class. So if I have not published this, to this class, I can do it, maybe after the class using the announcement. It also includes some other points of, critical thinking, collaboration, the importance of structure, and that's one big reason why I am teaching this class in synchronous mode is structure. Okay, because we are meeting every Tuesday and every Thursday at 9 a.m. That is structure, and if you can kind of build your other activities related to this class around this time, like I'm gonna start to review the material like starting at maybe 8:30 or 8 o'clock, and then I'll review the material after class. That is building your own activities around this class. Okay, so moving on to, so as we go, I will go, or I'll get back to this mind map, as we go. But just one more thing, okay? Just one more thing is, I do answer questions in my classes, but I may not give people a straight up direct answer most of the time, because I want to tell people where and how to find the answer instead of giving people the actual answer itself. I think this is college, right? So you guys are just a few more years from going out to work as a developer, or as a computer scientist, or computer engineer, or a mechanical engineer. No matter what you do, okay, you're still in the STEM field. And as a result, I think being able to think independently and being able to learn independently is very, very important. And that is why instead of giving people a direct, straight answer, I typically will tell that person where or how to find the answer. If that annoys certain people, just try to look at it, as not me intentionally trying to annoy people, because I really want to build up your skill to learn and think independently. All right, so having that kind of cleared away, the syllabus, watch the video of the syllabus, so I'm not going to talk about it much. So we are going to start with prerequisite check, okay? Most people in this class already have this cleared. If you see a point of 1 in the prerequisite check, then you are done already with the prerequisite check. On the other hand, if you see a 0, that means you have not met the prerequisite of CISP310. I have had people who have taken Java either on our campus or typically it's from another campus, from Sac State, because they only use Java, they don't use C or C++. That is not sufficient, okay? Because Java has no pointers, and in this class, in the second half of this class, pointers are going to be very, very important. So, not seeing any questions. All right, cool. So what I'll do is I'm going to get started. Okay, I'm going to get started with physical state, truth, numbers, and computers. So this is the slide, and if anyone is wondering how to read the notes, what I'll be talking about in the next lecture and so on, it's really just sequential order, okay, in the modules. So if you look at the sequential ordering of the modules in Canvas, that is typically how I do it. All right. So we'll start with this topic. And as we go, sometimes I will mention, comments from past semesters, just so that, sometimes it's useful. Most of the time it's not. All right. So starting with physical states. Physical devices are basically the things that we use to implement computers. In the earlier days of computer science, back at the end of World War II, there were electromechanical computers. If you have watched the movie The Imitation Game, Alan Turing, which is an actual historical figure, he is considered the father of computer science. So the computer that he helped build was a electromechanical computer. There were rotors. Rotors means things that turn. And the and then the rotor has contact points. So by rotating, a rotor can change which component is connected to which other component. Now, fast forwarding to present day, a very typical electromechanical component that can be used to implement a computer is a relay. Okay, so all you have to do is to look up 12-volt relay, and you will find lots and lots of pictures of what a relay looks like. So what a relay is it has a control terminal, and it has contact points. So basically, we are using a smaller electrical signal in order to change the connectivity of a potentially larger electrical signal. But the point is, we are using the same kind of physical quantity, which is in this case is electricity, to switch to control the flow of the same kind of quantity in physics, which is electricity. So let me check. I think I might have one more person who wants to get in. Alright, so I'm not sure whether that person is already in or not. I think that person is already in. Alright, so that's a electromechanical device. Now, why don't we continue to use electromechanical devices to implement computers? Well, the biggest thing is they're slow, and they're very power hungry, and they're huge. They're gigantic in terms of size. So we don't want that, right? I mean, if we were to use electromechanical devices to implement computers, you would not have a smartphone, period. Because let's check out what, well, maybe later on. Okay, later on we'll talk about this. But if you just look at a picture of a 12-volt relay, or any type of relay, okay, you can look for the smallest possible relay. It's still not that small. Okay, it is still taking up quite a bit of space as one single switch. So that's one of the big disadvantages of a electromechanical device. And then the other thing has to do with they're really, really slow too, because we are really thinking about like an electromagnet, energizing a magnet, and then the magnet will in return pull a reed from one position to another position, and when it switches all the way to the other position, then it will either break a connection or it will establish a connection. But the point is, it's really slow. I mean, you guys already know that conventional hard drives are much slower compared to SSD or solid state drive, because a conventional hard drive has a disk head that needs to move around when you're accessing different tracks on your hard drive. And that movement, that mechanical movement, is why it is so slow. Okay, things are measured in milliseconds. A millisecond is 1,000th of a second, and that seems to be pretty quick to us. But in the when you compare that with solid state devices, that is really, really slow, because solid state devices, you're talking about microseconds for really slow electronics, and you're talking about nanoseconds or even smaller when you're talking about really high-end top of the line type of electronics. So we're going to move on to vacuum tubes. So vacuum tube, this is a hyperlink to a Wikipedia page. So you don't really have to know a whole lot about these. I'm just giving you a historical record of what devices have been used in the past to implement computers. So vacuum tubes are much better compared to electromechanical devices because there's no actual moving parts. They're not mechanical. However, vacuum tubes also consume a lot of power, because you have to use a heating element in order to heat up metal so that electrons are free to emit from the surface of the metal. So each vacuum tube looks a little bit like a light bulb. Okay, it's not very bright. It doesn't need to be that hot, but it has to be at least glowing hot. So if you turn off the lights, you will see a very reddish, dim, glow to a vacuum tube. So that's a vacuum tube, and vacuum tubes do almost the same thing. You can use an electrical signal, in this case a voltage, to control the flow, which is the current of electricity. It's not bad for doing that sort of thing, except it is one, very power hungry, two, they're pretty big, and three, they're not really as fast as transistors, which we'll see next. Since we are on the topic of vacuum tubes, I just have to mention this. You would think that people are not using vacuum tubes anymore. Well, turns out that is not true, because I was looking up Bluetooth audio receivers. Okay, so if you have a cell phone and you have a really nice headphone that you want to use, and that particular headphone does not have Bluetooth built into it, you can purchase Bluetooth devices that can hook up to a regular headphone. Some of the higher end receivers like that actually can also use vacuum tubes in order to change the tone or the color of the sound. So vacuum tubes are actually interestingly still being used today, even though we're basically combining the latest and greatest Bluetooth technology with some really old electronic technology like vacuum tubes in order to retain some of the uniqueness of amplifiers that make use of vacuum tubes. I just find it to be kind of interesting. That's why I mentioned it. And I got some people typing. Maybe they're commenting on this. But since I'm not seeing anything posted yet, I'm just gonna move on. Oh, there we go. They're also still the gold standard for guitar amps. Oh, okay. I did not know that. Is that because of the tone or the coloring? They make warm sounds, or is it because they actually have actually have better spec compared to solid state amps? Okay, so it's because of the warmth. The loudness part, I'm pretty sure modern electronics or transistors can do the loudness part, but it's the characteristic of the sound. Yeah, okay, I get that. You can probably use a 20 band equalizer to emulate the effect of a vacuum tube, but I think some people just like having a vacuum tube on their amp because it really looks cool, by the way. All right, very nice. Yeah, exactly. Although they do get hot. I do have to emphasize that if you have a vacuum tube, they do get hot because they need to be at a higher temperature in order for electrons to be able to leave a metallic surface. Yep. Cool. All right, so we are now moving on to transistors. So transistors has been around. They have been around for a long, long time. Okay, I'm not going to talk about the doping process, or the distinction between a BJT versus a FET. BJT is a bijunction transistor, and then a FET is a field effect transistor, which for the most part we're using FET or FETs these days. So for transistors, they are in essence the same kind of deal as the other devices that we have talked about. You use one kind of physical quantity, in this case the flow and also the charge of electrons, to control the flow slash voltage of electricity. So the bottom line is, as long as you have valves or switches that utilize the same physical quantity in order to control the flow of exactly the same kind of physical quantity, you can probably use it to implement computers. So if you can make a valve that uses the water pressure to control the flow of water, you can probably use those, okay, a whole lot of those, to implement a computer. Kind of like, is it called redstone in Minecraft? So those can also be used to implement computers. So yeah, so we can use a lot of different things to implement computers. We are now moving on to section 2.2, which talks about physical states. So for the most part, in modern electronics, all we really care is what is the voltage at a certain point. If the voltage is high, and when I say high, it's not, doesn't mean like 110 volts. It just has to be higher than a particular threshold, and that threshold is getting lower and lower as we make transistors smaller and smaller. So if the voltage is higher than a particular threshold, we register that as a 1 or true. If the voltage at a particular point is below a certain threshold, then we register as a 0 or false. So that's how we make the components inside the computer binary, because all we really care is whether it is above a certain threshold or it is below another threshold. Those two thresholds typically are different, so there's a kind of no man's zone in between the two thresholds. But we are not going to talk about device physics in this class, so we're not going to get into that. So that is really a good portion of section 3. The top part of section 3 is what is true, what is false. Well, all that really translates to is above a certain threshold, it is true. Below a certain threshold, it is false. It's a meaning that we assign to a continuous or analog quantity that you can measure using a voltmeter. Okay. And it's just interpretation. Okay, the computer really does not have anything like true or false, because those are all abstract concepts. But when we implement computer components, we basically just assign meanings or semantics, of a to the criteria that we apply to these physical quantities. Voltage beyond a certain point, below a certain point. That's how we do it. Alright, so at this point we are transitioning a little bit to the use of a particular tool that you'll be using all the way in this semester. It's called Logisim. Don't worry, the lab that we're going to do today is going to help you understand what it is, how to get it, how to make use of it, and so on. So I'm not going to show you how to install it because of what I just said. And instead, I am going to run it so that we can see what it is and how we can use it to make the smallest component that we can utilize in a computer. So I'm putting into your view an instance of Logisim. Now, don't just Google Logisim and download it, because you have to use a particular version. You have to use the version that I have modified. So don't just download anything, because you're going to need a very specific version in order to do the homework for this class. There we go. So here's Logisim, and in Logisim it already has the concept of transistors. So I'm going to pull the transistors, and then we'll take a look at the schematic of a transistor. Schematic simply means the symbol of a transistor. So it belongs in, if I remember, wiring. So we're going to pull a few components here. So this portion of the screen allows you to look at all the different types of components that you can use in a circuit. So if you consider this portion, as the main editing area of your programs, this part here is showing you what classes you can use. Okay, what types you can use in programming. So in this case, I'm going to pull a power. So as soon as you click on a particular component, you are selecting a quote-unquote class, or you're selecting a type. And you don't have to drag. This is not a drag action. It's just a click. Move the mouse onto the other part. Let me zoom in first. Okay. So the other thing about Logisim is it doesn't have a very conventional user interface. Because conventionally in today's standard, when you want to zoom in, typically you type Control-Shift+, or something along that line. That doesn't work in Logisim. Logisim is a very old program, and the author stopped supporting it quite a while ago, but it is very functional, okay, for the most part. So if you want to control the zoom, it is down here. So you just have to click it to zoom in. And this is probably a good zoom ratio. I can probably get it one level deeper like that. All right, so this is the symbol, representing power, and this is the symbol representing ground. If you have taken the class in electronics, like ET, electronic technology, that is kind of helpful, but it's not a prerequisite to this class because this is the only class meeting that we are going to use, these particular symbols. After today, we're going to use something else. So don't worry if you're not very familiar with what is power and what is ground. One way to think about this is power, which is this symbol over here, the top one. It is the same thing as the plus terminal of a battery. And then ground is corresponding to the negative terminal of a battery. I'm hoping most of you already know, what is the plus and what is the negative terminal or the end of a battery. Because if people do not know that, I start to worry a little bit. Okay, and I think 10 years down the line, I think some of my students will not understand what is the plus or the negative terminal of a battery, because by that time everything is going to be rechargeable and the battery is built into the device itself, so no one will ever need to look at an AA battery and figure out, okay, how do I put this battery into the device, because the battery is going to be built into the device. You just have to hook it up to USB, I don't know, by that time maybe Z, USB Z, to charge the device. And USB-C already is not polar, which means you can plug in either way. So we are making devices as user-friendly as possible. So in 10 years time, when I refer to, oh, this is the same thing as the plus end or the positive end of a battery, people would just look at me blank and go like, I have no idea what you're talking about. Yeah, I would probably find that disturbing, but we are not 10 years from today yet, so I'm assuming most people still know what is the positive or the negative end of a battery. Yep, usually, yes, negative end to the spring side, but when you have coin type battery, it's usually the opposite. Yep. Yep, because with a coin type battery, the larger contact surface is the positive end of the battery, unlike in the case of a AA or AAA type of battery. Anyway, positive end, negative end. This is kind of the same thing as a 1. This is kind of the same thing as a 0. Okay, so think of it that way. This is the same, almost the same as a 1. This is almost the same as a 0. Alright, so once we have these, we're going to pull some transistors out. Okay, transistors right here. You would also notice that as soon as you click on a class or click on a device type, you will also see the properties or the default properties of an instance of that type. So it's okay either way. Okay, so right now I'm just going to pull one and put it on the screen. This is a transistor. So with a transistor, it has 3 terminals. It has 3 ends that we can connect things to. So let me see if I can point it somewhere else. So if you just hover your mouse pointer, over an end, now it doesn't show. Darn it. Okay. It doesn't want to show the nomenclature because it doesn't have any in this case. All right. That's okay, not a problem. So this is also, I'm going to show you how to find information on your own. If you need to look up and go like, okay, I cannot distinguish, which one is the gate, which one is the source, and which one is the drain. Okay, those are the 3 terminals of a transistor. So it has help. Okay, so you go to help, you go to library reference in this case, and you would notice that when you go to the help screen, it is organized almost exactly the same way as the tool, well, the class hierarchy over here. So if you find transistor under wiring over here, it would be the same over here. So you look under wiring, and then you look up transistor, click on it, and this is the explanation or the documentation of a transistor. So I would leave it up to you to find this piece of text when you have time to read through it. But for today, I am going to explain it. Okay, so let me get back into Logisim and I'll start to explain it. It is also explained in the notes, the written notes that you already can read from Canvas, and I'm assuming most of you are reading the notes, also, or at least have it open on the side. All right, so I am going to let Ben in. Yeah, well, that's why I keep telling people, I keep trying to remind people, okay, you need to follow the instructions, sign up and get onto the server. And I would spend the first few minutes of the class to do it. Of course, there are always people who might not have read the announcements. I'll put it that way, gently. Okay. Alright, so this is a transistor. It has 3 ends. The end that is the easiest to distinguish from the other two is this end over here. This is called the gate. Okay, so the gate is where the control signal is going. Okay, so the control signal simply means okay, I want to flip the switch. Okay, this is where you flip the switch. Okay, it is the gate. Alright, so I'm going to use a tool, the text tool here. The text tool doesn't really do a whole lot other than just for documentation. So I'm going to use the text tool to help me identify which end is which end. Okay, so this is gate right here. And you can also see between these two, you can distinguish these two because of the tiny little arrow here. It looks like a greater than symbol, but it's really intended as an arrow. So you can go to YouTube, Ben. Alright, so it looks like we still have a limitation in terms of how many people can join, even though I turned off the ability to use voice on Discord, which is kind of annoying. I'm going to have to look up ways to get around it. Oh, okay. I can do that after class. I got 1 or 2 nitro that I can use. All right. I'll look into it. But for today, we're going to use YouTube for the quote-unquote overflow. Alright, so getting back to it, how to read a transistor. So between these two terminals, the one to the left and the one to the right, it looks like these two are very difficult to distinguish. But that is not the case because of the arrow here. So if one is called drain and the other one is called source, which one do you think should be labeled source and which one do you think should be labeled drain? Yep, that's right. Source, and then this is the source and this is the drain. Very good. Okay, so the arrow is intuitive, right? So now we're going to label it. This one we label it as the source, and this one we label it as the drain. There we go. I'm just going to move the label a little bit so it's nice and neat. There we go. Alright, so this is how we identify the 3 different terminals of a transistor when we are only looking at a schematic. Now this is called a schematic because it is a symbolic representation of a device. It is not even close to what it should look like. Okay, because if you go out and buy a discrete component, in other words a single transistor, it's not going to look like this. Okay, it's probably some kind of packaging with 3 pins. Now these days with surface mount components, there are lots of different shapes, lots of different sizes and so on. So it's really hard to tell, what shape, a transistor should look like. This is also a good time to mention that a single transistor like this, in in a modern processor is only 5 nanometers across. Yeah, we are talking about 5 nanometer now. AMD has 7 nanometer process, and I think Apple has the 5 nanometer process, if I remember correctly. So the new chipset that Apple put into their iPhones and iPads, each transistor is only 5 nanometers across. With the AMD processors, the latest AMD processors are they use the 7 nanometer process, which means each transistor is about 7 nanometers across. So it's really fascinating because not too long ago, now when I say not too long ago, to you guys it's a long time ago because I'm quite a bit older than most of you. So back in 1990s, okay, the early 1990s, people thought that they would not be able to make transistors smaller than a micron, okay, just in one dimension. So a transistor would be about 1 micron by 1 micron. A micron is 1 micrometer. So at that time, about 30 years ago, people thought it would not be possible to make transistors any smaller. Guess what? Not only did they continue to make transistors smaller, but in 30 years of time, they are now making transistors that are 5 nanometers across. So if you compare 1 micron to 5 nanometer, we are talking about 200 times. So transistors are now 200 times smaller than what we thought was possible 30 years ago. That's really interesting progress because besides semiconductors, electronics, and stuff like that, you probably would not find this kind of advances in any other fields in terms of science and engineering. So it's really quite fascinating in that way. Cool. All right. So now we're going to say we'll take a look. So I'm going to select the component, and we'll take a look at the properties of this component. So it has a few things. We are not going to mess around with data bits for now. These two, phasing and also gate location, they are really here to control the how a transistor appears. So if you want to flip the gate to be below on the other side, you just have to go to gate position and change it to bottom like that. So, well, that's not what I want to do. So Control Z is going to undo. So at least, Logisim still has Control Z for undoing stuff. Yep, Moore's Law is fascinating. Okay, does everybody understand what is Moore's Law or not? Because I think this is a good time to explain Moore's Law. No. Okay. Well, you can always look it up. So in essence, Moore's law says transistor would get halved. The size of a transistor gets halved every 18 months. Every year and a half, the size of a transistor will be halved in an integrated circuit like a processor. That's the bottom line. Okay, whether it's 18 months or 19 or 17 months, it really doesn't matter because the order of magnitude is right. Okay. So if you think about it this way, let's just say that we are talking about 24 years ago, okay, to make it even. So now the first question is, how many 18 months can we fit in 24 years? No, not 8. Because I'm asking how many 18 months can we fit in 24. So we are talking about 24 divided by 24 years, 24 divided by 1.5. 16 looks about right. Okay, 16 is correct. So you might think, oh, does that mean we are the transistors are getting to 2 times 16, which is 32nd. 1 over 32 of what it used to be 24 years ago. Nope. We are talking about power. Okay, so we are talking about according to Moore's law. Okay, if Moore's law is 100% correct, then a transistor today is going to be 1 divided by 2 to the power of 16 compared to a transistor 24 years ago. Yeah, so that is a huge amount because it basically means every 18 months, every 1 year and a half, the size of a transistor will be halved. Okay, and it has that exponential nature to it. Um, and people thought that Moore's law we would have run out of steam back in the early 90s, and guess what? We're still going. We have different techniques to fit more transistors onto the same area on the chip these days. So they have quote unquote 3D circuits now on the processor chip. But the idea is we are still packing more and more transistors per square area on the chip. So that is that to me is truly fascinating. So, all right. So if you go back to the text channel, it talks about how the speed doubles. That is because when the transistor shrinks in size, shrinks in in area, the speed is also increased because how fast we can switch transistors depends on two main factors. The first one is the surface area of the chip, okay? Because the bigger, the more surface area it has, the more charge it can hold, and therefore it takes more time to change the state, of the quote unquote charge of that particular surface. So the area of the chip has one impact on the switching time. The second one is the voltage, okay? Because if you think about the old TTL, okay, transistor to transistor logic, that's what TTL stands for. TTL is a 0 to 5 volt standard. 0 is when something is off, 5 volts is when something is on. So that's a pretty big voltage swing, okay, and it takes more time in order to change a capacitor, so to speak, from 0 volt to 5 volts. These days, we are talking about less than 1 volt on some of these 5 nanometer process devices. So the amount of voltage swing you have to change is also smaller, and that also increases the speed of the transitions. So both of those contribute to why smaller transistors are faster. Okay, and that's also very interesting. Ryan in the text channel mentions we are now running into physical limitations because of quantum physics. Because transistors, with this type of transistor, there's an insulation layer. If you look at it, okay, I can explain that if I zoom in. This is the best I can do because I think 400% is the largest the maximum I can use to zoom in. So there's a little gap, right? See this plate here? Okay, if you think about this as the side view of a transistor, there is a plate right here, and there's another plate right here, and then in between is not an air gap. That is a metal oxide gap in between. Typically, it's metal oxide. Basically, it's an insulator. We are making this particular layer so thin now that quantum physics, is kicking in, and electrons can basically teleport themselves from the top plate to the bottom plate now. And that's basically as thin of an insulation layer that we can make it, because any thinner, we can make layers that are thinner, but it's not going to be useful because it's no longer an insulator, because electrons can just teleport themselves, because of quantum physics, to the other side. Yeah, bleeding through. Thank you. Technical term. But it's about quantum physics, okay? And if you have not taken a class in quantum physics and you have time or you're curious, I highly encourage you to take a class in, or at least read some Wikipedia pages on quantum physics, because I think at some point computer science people really need to understand quantum physics, because that's the future of computers. Not yet, but I think in your lifetime for sure that quantum computers will become reality. Yep. Well, the thing is, we don't even know. If somebody has already built a quantum computer, they're not going to let the rest of the world know about it, because the first person or the first organization that has a working quantum computer is not going to let the rest of the world know about it, because quantum computers are extremely, at least in theoretically speaking, they are very efficient at cracking encryption. So if you have a machine that can crack encryption, basically any type of encryption today, you don't want to let people know that you have that capacity, because knowing that capacity usually does not mean good things will happen. Yeah, very, very bad things will happen instead. So we have no idea. We really have no idea whether people already have these things implemented, because they might be just quietly decrypting communication instead of advertising to the entire world and say that, guess what? I can decipher everything you guys can encrypt now. Yep, especially for smaller countries and smaller organizations, they definitely don't want to attract attention like that. Sounds like a good premise for a new movie, I think. Anyway, all right. So now that we understand the the terminology of a transistor, now we're going to look at the first attribute of a transistor. This is a p-type, okay? And if you click on the drop-down box, you can switch it to n-type. You go like, whoa, hold on a second here. What just happened? Let me switch it back to a p-type. So you can see that with a p-type, there's a tiny little bubble right here at the gate. And if it is an n-type, there's no such bubble. So that little bubble is the symbolic negation. In other words, if you see a little bubble like this in a schematic diagram like this, it means negation. It means, if it's true, turn it into a false. If it is false, turn it into a true. Okay, so what does that mean? What is it doing here? And also, how do we connect transistors, to power and ground? Well, as it turns out, for a p-type transistor, which is this one here, the source should connect to power, or the higher voltage. If this is an n-type transistor, then the source needs to connect to the lower voltage. So let me do a trick like this. So you can just select an area by dragging your mouse. So once you select an entire area, everything within the area will be selected. And then you can do a Control D for duplicate. So now I have a duplicate of the original, and they are basically, you can look at these two as objects. Okay, this is one object and this is another object. Not quite an object, because they're independent tiny little things, but we'll go ahead and say each one is an object. So if I just look at this one and turn it into an n-type, this makes it easier to see the differences between a p-type, which has a little bubble here, and an n-type, which does not have a bubble here. So remember what I said earlier. The gate is where the control signal is. So typically, intuitively, when we say 1, it means true. And most people associate true as, let's go ahead and turn on something. Okay, so that is the assumption being used here. Okay, well, when this particular plate here has a 1, it is turning on something. If it is a 0, it's turning off something. So what this means, is in order to turn on a p-type transistor, you need the gate to be a low voltage, or to be 0. To be, in our context, we can just call it 0. So in order to turn on the p-type transistor, you need gate to be a 0. And when I say turn on something, it simply means allowing things to flow from source to drain. Okay, so you're basically turning on a tap. You're opening a valve. That is what I mean when I said turn on something. And in order to turn on an n-type transistor, you just need gate to be 1, and it will allow things to flow from the source to the drain. Okay, so now we're going to build a little circuit here, and as I build a circuit, you can ask questions, but for the most part, I'm not going to talk much when I'm building the circuit here. So we need 2 of these. Okay, and we need both of these to orient in a way where the source is pointing up. Now you can also multi-select things like this, and okay, I don't need the lettering anymore, so let me get rid of these labels. So select and then click the delete key will delete stuff, just kind of as you expect. There we go. All right, so you can actually do a multi-select, which is click and then a shift click, sorry. So click and a shift click, and you have now selected multiple things. Now, the multiple things that you have selected, as long as they share certain attributes, you can change those attributes at the same time. Because both of these are p-type transistors, I can turn both into n-type transistors if I want to. But that's not what I want to do. Because what I want to do is to have the source, which is to the left-hand side, to point up. So I have to change the phasing instead. Right now it's facing east, which is basically where the arrow is facing. So I need it to be facing south in order for the drain to be up. So that's exactly what I wanted to do. And positioning within a schematic doesn't really matter because it is just a symbolic representation of how things are connected. So whether you want to drag it down a little bit more or a little bit more to the left doesn't make any difference. It really is just, do you think it looks nice from your perspective? That's basically it. And then with this one, if I want it to look nice, I can also have the gate to point to the right hand side instead of the left hand side. So here I can now go to gate location and flip it to the right like that. Okay, now this part is entirely optional because it really doesn't change how things are connected, because all of these things, none of these is connected to anything else. So with a p-type transistor, we need the source to connect to a high voltage, basically to a 1. With an n-type transistor, we need the source to point to the lower portion, which is the 0. Okay, so in this one, I can change the rotation first or change the facing. So this time I want it to face north because I need the source to be closer to ground. And we will have one more of these things. So Control D, once again, duplicate. So whatever you have selected, it will duplicate the entire selection. So now I got all of the transistors done, and I can now make connections. So in order to make connections in Logisim, you want to make sure that you're using the selection tool instead of quote-unquote the poke tool, which is a finger to poke at things. So you want to make sure that you have the selection tool, and then what you do is you want to hover the selection tool on a particular component until it changes and have a little circle surrounding where you are hovering over. Because if you're not doing that, it means you're not getting to a point where you can make connections. Now let me point out what I mean by that. Look at the ground. Look at the power symbol here. Okay, so most people would think, hey, I can connect to here or here or here. That is not true, because the only point you can connect to is right here. I did not click anything. I was simply moving my mouse to hover over a particular point. If it changes to a bubble or if a surrounding bubble appears, it means it is a connection point. Everywhere else is really just part of the picture. It's not connectable. So with a transistor, it is a little bit more intuitive. Okay, this is a connection point, this is a connection point, and so is this. So you can start with a connection point. You can draw a wire, and you can go across and then down. And if I need both of those to connect to here, I can now make a connection from here to here. Now you can see that at the moment I make the connection all the way up to the power symbol, the big dot appear. Okay, the big dot here is meaning that all 3 points are connected. Now, if you want to make sure that all 3 points are quote-unquote electrically connected, you can change to the poke tool. This is called the poke tool. And just poke, anywhere on the wire. And then the entire wire is going to highlight. Now, it also labels 1 because it's true, because it's measuring a high voltage. That's fine too. But the idea is, if you use the poke tool, you can see whether the connections are connecting the way you want it or not. Okay, so it's a pretty useful tool for debugging connectivity of a circuit. Okay, so I need the bottom to be connected as well, like that. And then I need this to connect to here, I need this to connect to here, and I need this to connect to here. Alright, so I have the circuit almost done, but not entirely. because right now I also need to. So if you think about this as the body of a subroutine, I have the body of the subroutine written, but a subroutine that only has local variables is not going to be very helpful, right? Because you need input and output. You need to use parameters to send information into a subroutine to process, and then depending on what it is processing, sometimes you can use a return value to return the result of a subroutine. Other times you need a pass by reference parameter to get the result out of a subroutine. So in the case of a circuit in Logisim, we also have input and output. I would just use these two. Okay, this is an input pin, this is an output pin. So square is input pin, and then circles are output pins. So here's an input pin. We need two input pins, and we only need one single output pin. Now, once you place it in the circuit, you can always move it somewhere else. Okay, so don't worry if that is not exactly where you want to put the component. Like this one, I can move it down here somewhere. Okay, it's not too important at this point. So let me finish the circuit here first. So I'm going to connect this to here and also to here. And then for this one, I wanted to connect to here as well as here. So the first one is here. Okay, that's pretty simple. So if I want to connect to here, there is a way to do it, which is to bring the wire around the entire thing and then put it over here. So this way I don't have to overlap that wire with any other wire in the circuit already. But that's really not necessary, because I can actually just have it to fly over a wire like this and make a connection on the other side. So you can see how in some cases it will give me a bubble like this to mean that everything is connected, and in other times it does not give me a bubble, which means one wire is either flying over or flying under the other wire, but either way they're not connected. Alright, and if you use the poke tool, it will be very clear, because if you use the poke tool to poke on this wire, you can see the highlighted portion, and you can see the vertical segment of this wire is not a part that is also highlighted, because these two, this one, this wire versus this wire over here, they are not electrically connected. One is flying over or under the other one. So keep that in mind as you draw your circuit. And the output pin is going to connect to here. There we go. So now we have a circuit that makes use of two p-type transistor because they got the bubbles, and two n-type transistors over here because they do not have the bubbles. And what is also important to remember, I said this already at least twice, so this is the third time I say it. A p-type transistor needs the source to connect to the high voltage, and an n-type transistor needs the source to connect to the low voltage. Okay, so the orientation of the transistors is very important in this case. Okay, so what is this circuitry going to do? The notes already has documentation, so everything that I have said up to this point is already in the notes. Okay, so you can always refer back to the notes if you want a written version of what I have said and also what I am about to say. Alright, so we're going to look at this, and I'm just thinking about how to reason out the connectivity. So this is what I'll do. First thing is I will label the input pin and the output pin so I can refer to the pin. Okay, so the label of this one is X, and this is Y, and I'll call this one just output. Okay, so there we go. And then for the transistors, I can also give them names. But as you can see here, they don't have a label, so which means you're gonna have to use just a text tool, general text tool, to give these guys names. So I can call this one Q1. It's just a convention to use Q as a prefix for transistors in the circuit. Don't ask me why, because there's no Q in transistor. But that's the convention. So Q1, Q2, Q3, Q4. There we go. Okay. Alright, so I'm going to turn off simulation for now. So to turn off simulation, you go to Simulate as a menu, and then you click on Simulation Enabled. So what that's going to do is it will toggle the checkbox over here. If it's already enabled, it will turn it off. If it's already turned off, it will turn it back on. So I'm going to turn it off, and I will also do a reset simulation. So this way there is no coloring of the wires to interfere with our manual interpretation of what's going to happen. Alright, so well, let's just look at this particular configuration and find out what output is going to be. Okay, is output going to be a 1, a 0, or something that is not determined? Alright, so that's what we're going to do now. And all we need to do is to analyze what is happening with each of the transistors. Okay, because we want to see eventually whether output as an output pin, is it eventually connected to power, or is it eventually connected to ground, or is it not connected to either one, where the output is called basically it's called high impedance output. It is not actually, it doesn't have a state, it is undetermined in that case. Okay, look at it as a unspecified return value in a C subroutine, which is typically a bad thing, but as an electronic circuit, sometimes we actually want circuit to do stuff like that. So let's go ahead and do a quick analysis. And I'll do the analysis using the text label over here. So I want to know whether Q1 is on or off. Okay, now remember, when something is on, it means it is allowing flow. If something is off, it means it is disconnecting, it is not allowing flow. So what about Q1? Is Q1 turned on or not? Is it allowing flow or not? Yep, you guys are correct. So Justin and Alexander are correct. The Q1 is on. Okay, so Q1 is on. And I guess that would mean Q2 is also on, right? Because Q2 is also experiencing a 0 at the gate. So we'll document that too. So Q2 is on. So at this point, we have a pretty strong suspicion that the output pin is connected to the power symbol. But it doesn't hurt to also check out the other two transistors. So we'll also check out Q4. Now I skipped Q3 first, but let's check out Q4. So what about Q4? Q4 is an N-type transistor, which means in order for the N-type transistor to turn on, gate needs to be a 1. But gate is a 0 for Q4, so Q4 is off. And the same applies to Q3. Q3 is also off. Alright, cool. Thank you. Not sure about Justin's 3/4 off. It's either, oh, okay, I see. It's not 3/4. Both 3 and 4. Both Q3 and Q4 are off. Okay, got it. Gotcha. There we go. All right. So knowing the state of the transistors, now we want to see, whether output is a 1, a 0, or undetermined. So we track down, output. We follow the trace. We go like, okay, it can go, in both directions. We'll explore the top direction first. Q1 and Q2 are both on, which means, these two are connected. These two are also connected. So that means, output has basically two paths to connect to the power symbol, and output is going to be a 1. But before we say that it's going to be, it's a 1, it's good to make sure that it's not connected to ground. So we look at Q3 and Q4, they're both off, which means this is disconnected, this is also disconnected, which means we are basically double sure that there's no path for output to connect to ground. So as a result, when X is 0, Y is 0, output is going to be a 1. Are we good so far? All right. Cool. Very good. All right, so I'm going to take remove these components. Remember, everything is being recorded on YouTube's side, so it's not going to be a big, huge problem. Okay, do we need to just memorize that the transistor gate is open if it's getting a 0? It depends on what type of transistor, because an N-type is open if it is a 0, but an P-type is going to open when gate is a 1. So let me let me get back to the point that I was trying to make earlier. This is where you find the documentation. And by reading through the documentation, it basically just repeats what I said, okay? But in order for it to sink in, you can do a review after the class, so that it sinks in better. All right, yep, there are only two types, P and N. And the P and an N refers to how a semiconductor component is doped. That's how we make semiconductors. Yeah. Not going to get into the physics of a semiconductor device here. It's really quite fascinating. I was trying to understand that when I was in 4th grade. It took me probably a month or so, to finally understand, the general idea of how a p-n junction works. But it was fun. It was fun to try to figure that out. Okay, so anyway, we are now here, and we're going to change the output. Let's just say one is 1 and the other one is a 0. So now we want to find out what is going to happen to the output. Okay. I wouldn't say they're inverses of each other. And Justin is correct. The output is still a 1. How did I change it? You use the poke tool, and once you use the poke tool, you can click on a pin or input pin to be sure, to change the state of the input pin. So you can see how, by using a poke tool, I can now, change the state of an input pin. There we go. All right, so now let's go ahead and analyze again. You guys, some of you already got the result correctly, but we're going to analyze it regardless. All right, so we'll analyze Q1 first. So Q1 in this case is off, and Q2 is on. Q3 is off, and then Q4 is on. No, I got it the other way around. So I think Q3 is on, and Q4 is off. There we go. All right. There we go. Thank you. All right. So why? Well, that's because Q1 is a p-type transistor. The little bubble here says if the input is 1, then it is turned off. That's why we have a little bubble. The same one is going to Q3, but Q3 is an N-type transistor without the bubble, which means when the gate is a 1, the transistor is on. It allows flow to go from source to drain. What about the input pin of Y? Y goes to Q4, and because Q4 is an N-type transistor, when the gate is a 0, it is off, and therefore it is disconnecting. And Y also goes to the gate of Q2. Q2 is a p-type transistor, and the p-type transistor is turned on, allowing flow when the gate is 0. That's why Q2 is on. So the question is, what should be the state of the output pin? So once again, we analyze the output pin. It goes in both directions once we get here, but we only need one path to connect to power in order for the output pin to be connected to power. So we know the output pin is connected to power, but we also want to double check and make sure that the output pin is not also simultaneously connected to ground. So Q3 is on. Okay, so this particular transistor is on, but because Q3 and Q4 are in series, it means both of them need to be on in order for output to find a path to go to ground. Because along the path, if at least one of these two transistors is off, then we do not have a path for output to go to ground. In this case, Q4 is off, so that is cutting off this entire path, and that's why output is also going to be a 1 in this case. So the output is 1, that is correct. So that would also explain why this configuration would also have the output being a 1, because the circuit for the most part is very symmetric. So if I just flip the output pin so that 1 is, so that X is a 0 and Y is a 1 this time, I just have to kind of invert the state of all of these transistors, but we still end up with one path from output to power and no path going to ground. We are just flipping between which one is on and which one is off. So the only time when we have output being a 0 is when X and Y are both 1s. There we go. But we want to know why. Okay, so we're going to go analyze the states of the transistors just so that we know exactly what is going on here. So going back to the text tool. So Q1 is off this time. Q2 is also off because both of the P-type transistors have an input of a gate connected to a 1. And both of the N-type transistors are on this time because both of them have a gate being a 1. So Q3 is on and Q4 is also on. So in this particular scenario, if you track down output, there's no path to connect to the power pin here, which is basically a 1. And both Q3 and Q4 are on in this case, which means the two switches that are connected in series, because they're both on, now they complete the path for output to go all the way to the ground pin over here. The ground pin, by the way, is just 0. So output has no way to connect to a 1, but it does have one path to connect to a 0, and that's why output is going to be 0 in this case. So in this particular configuration, output is a 0. So I have Justin is 100% correct. I have just described a NAND operator or NAND gate. Okay. Now whether we want to call this a gate or an operator depends on, are we looking at this using a graphical representation, or are we looking at this using a text representation? So let me summarize. Okay, give me a second here to get to a text tool that is called mousepad. I'm using Linux, by the way, so I don't have notepad. Instead, I have mousepad. So in this case, I have X and Y being inputs, and I want to look at what the output is. So I'm just summarizing what we have said already. If X is false, Y is false, the output is a 1. If X is false, Y is 1, the output is a 1. If X is 1, Y is 0, the output is a 1. And the only time when we have an output of a 0 is when both X and Y are 1s. So that captures the 4 different scenarios that we have gone through analyzing the circuit. So when you look at this and go like, that looks like AND, but it's kind of the opposite of an AND. So using a different truth table, okay, we got X, we got Y, and this time we have the negation of X and Y. So for the time being, I'm still using the C notation because it is, I'm assuming everybody should be able to read the C notation at this point. So we look at this, go like, okay, that's going to be a 1, 2. And if we have this, and that is 0, then we're going to have a 1. And if we have both being 0s, then we have a... Oh, okay, never mind. If we have both X and Y being 1s, then the expression is going to give us a 0. So without looking at the circuit and just looking at the C expression over here, are we convinced that this is the truth table for this specific expression? Do we have any questions about this part, which has nothing to do with the circuitry? Cool. All right. But when you look at the truth table, of the circuitry, it has exactly the same value. So, the output of the circuitry has 1110 corresponding to exactly the same input configuration. So this is how we can say, hey, the circuit that we looked at, okay, which is right here, is implementing the same thing as the negation of an AND, which is called a NAND. N-A-N-D. The first N represents negation. Okay, so getting back here, I'm not going to call this the negation of an AND. Instead, I'm going to say this is X NAND Y. So that means this particular circuit configuration is performing the same thing as a NAND, and we call this a NAND gate. Okay, so whether we use the term gate versus the term operator depends on if we are using the circuitry schematic context. Then most of the time I would use the word gate, okay, to represent to refer to this thing here. If we are using a text context, then I would refer to this as an operator. But they are really the same thing. They're really the same thing, just called slightly differently when we have a different context. Okay, so most of you are now thinking, okay, well, it doesn't seem to be very useful because we don't have an actual operator performing NAND, because if we want to represent NAND, we need negation and logical AND, which is not exactly, user-friendly, right? I mean, why would we want to understand NAND? Well, as it turns out, all we need is NAND. We don't need no stinking NOT, we don't need no stinking AND, we don't need no stinking OR. If C++ only has NAND as a Boolean operator, we would have been fine, because we can use NAND to basically implement the other operators that we are familiar with. So that portion is mentioned down here. Okay, NAND is all we need. So in order to simulate NOT, so if we want to represent the negation of X, we just need to say X NAND X. It means exactly the same thing. If we want to implement AND, so X and Y, this is the mathematical symbol for AND. So X and Y is the same thing as X NAND Y, NAND, X NAND Y. If we want OR, this is the mathematical symbol for OR. It looks like a little V symbol here. So if we want OR, we can just use X NAND X, the whole thing, NAND Y, the whole thing. Okay, so it's really kind of interesting because it's one single Boolean operator that can be used to basically implement all of the other operators that we are familiar with. We are running out of time in the lecture, so what I'm going to do is to show you guys how to do the lab. So the lab is not opened yet. I did not take row today, I forgot. I'm going to have to set up an alarm to take row. But that's okay, I'm going to use the lab for that purpose. So people who do not participate in the lab is going to be considered as missing the class. Alright, so here's the lab. And the lab is just for setting up Logisim. Okay, I got a message here. Would the truth value of the test pin be the same at any point in the circuit? Okay, so let's go back to that one. Let me turn simulation back on. So simulation is now back on, and as soon as I change the state of an input pin, there we go. So this is the time you can basically tell, if I turn one of the inputs into a 0, the output is going to be a 1. So I'll just do it here like that. Okay. So does that answer the question, Ian? Basically, you need to look at the entire conductor. Okay, so if you poke on this, okay, use the poke tool. If you poke on this particular conductor, it connects to this point, as well as this point, as well as this point over here. So this is called a node in an electrical circuit. It's called a node, which is equivalent to one single piece of conductor on a circuit board. So are we good there? Cool. All right. And we got one more person typing. And meanwhile, I'm going to go back to here. The output is basically the result of where the output is connected to either. Well, yes. Yes, in this particular circuit it is. Alright, so I am going to edit the lab because it does not have the right time, due date. So there are a few things you should probably pay attention to, when you are doing a lab activity. The first one is, typically speaking, I allow multiple attempts, and I will keep the highest score. So the idea to do this is, when people get an answer wrong, they will have a second chance, a third chance, a fourth chance to get it right. And the idea is, I want people, if they get something wrong, I want them to be able to study a little bit, think a little bit, figure out what might be the correct answer, and then try again. Because I don't want it to be punitive where, oh, you got it wrong, you're going to get a 0 for that, and that's permanent. I want people to think, retry. I do not want to encourage people to abuse this ability and just go like, oh, so that means if we have multiple choice, then I can just answer one question, try out all the choices until I get the right one, then I move on to the second one and do exactly the same thing. So that approach may work in certain type of labs, but it would defeat the purpose of the lab entirely, which is okay with me because eventually it is not my grade in this class. Okay, but if people really want to understand the material, I would probably discourage people from using that particular approach. Let students see their quiz responses. Incorrect questions will be marked in student feedback. I turned it on just so that people can see it, so now they can say, okay, I think I misunderstood something. Let me read the notes again, try to understand it, and then I'll try again. So once again, abusing this feature of a quiz is not going to help the person who is doing the abusing. So show one question at a time, no big deal. This one you need to know is Logisim. I'm going to put it into the text channel just so that you guys can get it from there. This is the key where you need to type in order to participate in this lab, which basically means people who are not a part of this conversation are not going to know this. I mean, they can watch the video and go all the way to the end and know that too, but extra steps. Okay, so we have I'll make it due today at 1:20, I think. Yep, okay, so it's August 24th at 1:20 p.m. I know there are 2 lab sessions, so if we were on the ground on campus, I would have basically 2 sessions. There'll be one batch of people in the lab for the first lab, and then we'll have a different batch of people for the second lab. Now that we are actually just online, I'm just going to combine both labs, so you guys can all start at the same time, and everybody has twice the amount of time to complete the labs. So now I'm going to do a save and publish, which means as soon as this appears, you should give it a try and see if you can get into the lab. I'm still screen sharing because just in case we have any question that I can answer for the entire class, this would still be useful. Anyway, we could make it due at the end of the day. No. No, this is a synchronous class, so the lab is synchronous. It is as if everything is on campus face to face. So nope, the due date or the due time is 1:20 p.m. That's almost like 3 hours. I mean, you don't need 3 hours for this lab. We got a few people typing. I'm still screen sharing. Alright, so we have confirmation the lab is working. Lab is asking for an access code. Yes, that is why I typed Logisim up there. Okay, so looks like everything is working. Sammy, you need to change your nickname. Okay. So that I can see your full name, not just your first name or last name. There we go. Um, no, you do not need to remain on Discord, even though you might want to keep an eye on the text channel. Because when some people ask questions, they might ask it in the text channel. So by answering one person, if you keep an eye on the text channel, you might get the answer too. Next one is, so every Tuesday and Thursday until the end of the semester, both groups will have lab from 10:30 a.m. to not 11:50 p.m. It's not 11:50 a.m. It is 1:20 p.m. because both basically I just give you twice the amount of time. Yes, I am combining both labs. So the duration of the lab is now basically basically the 3 hours after the lecture. And then office hours is also right after that. So we have a pretty long, structured time frame for you guys to do stuff and ask questions. Permission code stuff, I have to take a look at how many people are not in class and how many people dropped already. So I will handle that, when I have time to kind of look at enrollment information for this class. Cool. All right. So anything else? You can use direct message to ask questions about the lab, or you can use today's date channel to ask questions. Either way, it's fine. I think we are yeah, sort of on your own. So the question, so the statement is, so we do the labs right after the lecture on our own. Yes, so it's kind of mostly on your own, but I'll be online, ready to answer questions. But once again, the way I answer questions is usually I tell people where to find the answer or how to find the answer and not the answer directly. Yes, so the lab will give you the instructions to install Logisim and also to use Logisim for various things. Yep. Yeah, it might complain. It's okay. It's gonna be fine. Your computer blocked the download. You might need to turn off your virus checker or give it an exception. See if you can make an exception for Logisim. Yes, the download would also work on a Mac. It's really just a jar file. It's basically if you have Java installed, it should work. All right, so I think we're getting into the specifics of the lab. We probably don't need to do screen sharing or my voice at this point. So I'm gonna turn off streaming and also my voice connection, but I will participate in the text channels and also the direct messages at this point. So I will see you guys on Thursday, even though I will still be online for the next few hours.